Good morning and welcome. Today, I'd like to speak about INCA, the Integrated Catchments Model. INCA is one of a family of water quality models that are in relatively widespread use. My rationale for presenting this lecture is twofold. One is to give you a more in-depth understanding of one particular water quality model. And the second purpose is to provide a little bit of context and background for the lab that we will have next week, where we use the nitrogen version of the model to do some scenario assessments based upon the PERSiST lab that you did last week. So in the lecture today, I divided into 4 blocks. I tried to put the model and water quality modeling into a bit of context. Then I'll discuss some of the design decisions that went into the INCA model, talk about versions of the model, which pollutants can be simulated, and some of the design decisions about the pollutant simulations. And then finally, to present some model applications, so some fairly generic ideas of how water quality models can be used to answer relevant questions. Briefly, INCA is a catchment scale water quality model. So it simulates both terrestrial and in-stream processes and transport of selected pollutants, generally those that are relatively high priority and of management interest. The model's been applied to relatively small catchments, say on the area of 1 to 10 square kilometers, up to entire river basins such as the Ganges and the Brahmaputra in the Indian subcontinent. The model's dynamic, so the results change over time. It's semi-distributed, so it's possible to predict values or project values at multiple points within a river network. And it operates at a daily time step, so it is able to simulate some kinds of event responses, like to say pollutant spills or to deposition or to changes in seasonality, such as changes in snow dynamics. The model is a decision support tool. It's been most often used in the UK for assessing water quality questions. It's also been applied in Fennoscandia, in Canada, and quite a bit in the Indian subcontinent. Conceptually, the INCA model is quite similar to other widely used water quality models, for example, SWOT and HYPE. So pretty much everything I say here about how the INCA model works can also be applied more or less to other widely used water quality models. And where there are big differences between the models, I'll try and mention it. So I'd like to just try and contextualize INCA and other water quality models from a DIPSR perspective. Models like INCA provide dynamic simulations of state, specifically water quality in rivers and lakes. And one rationale for doing these dynamic simulations is to support both the design and the assessment of responses to control pressures. The simulations may also give insight into drivers and possible policy responses. But the goal of the model is very much to try and give additional insight so as policy responses can be evaluated and assessed. Models such as INCA are also very relevant for the Sustainable Development Goals. I could find 5 goals for which water quality models are directly relevant. Clean water and sanitation is probably the most obvious one, but the specific targets that water quality modeling support include sustainable food production systems, to reduce water pollution-related deaths and illnesses, safe and affordable drinking water, improvements in water quality, integrated water resource management, and environmentally sound management of chemicals and waste, and finally, sustainable use of inland fresh waters. So models certainly play an important role in assessing progress towards the SDGs, and they can also play a useful role in determining whether or not nations are setting policies that move in the right direction to achieve the SDG goals. So with that little bit of context about water quality models, DPSIR, and the Sustainable Development Goals, I'd now like to talk about some of the aspects of the design of INCA, some of the decisions that went into establishing the model, which highlight perhaps some of the strengths and perhaps also weaknesses. So the first design goal of the INCA model was to produce a dynamic model. The model was first published, first used in the late 1990s, and the model was developed as a sort of a follow-on or response to steady state models then in use for nitrogen, primarily nitrogen simulation. So steady state models, as you'll remember, are not time varying. They typically are relatively simple. They don't give any ability to, say, assess time it would take for a response to occur to a change in emissions or a change in loading. So from a decision support perspective, it's certainly useful to have a dynamic model that can indicate the time it might take to respond to a management action. And that was very much the idea behind the development of INCA. It was originally developed in kind of an environment of concern over eutrophication from primarily nitrogen and concerns about, say, exceedances of critical loads and eutrophication of upland forests, ongoing eutrophication of surface waters due to nitrogen pollution in lowlands, and also concerns about groundwater nitrate contamination. So with all of these pollution situations, there's likely to be a lag time between the time that a measure is put in place to control emissions and the time that an improvement is seen in state. So one of the key goals of dynamic modeling was to try to quantify or make some sort of assessment of the likely time it would take between implementation of a measure and seeing an improvement in state. The second design goal was to make a flexible model. So to make a model where there were lots of parameters that could be tuned and assessed. This is one design philosophy. Other models make many parameters fixed, say based on literature values. The idea behind the INCA approach is that parameters such as rate coefficients, while they can be measured in the lab, these measurements can be difficult to apply uncritically to the field. So by making a model with a large number of free parameters, it opens the door to calibration in a number of different situations, gives some possibility to assess sort of sensitivity or what controls the model response, maybe also to make estimates of uncertainty in model predictions. And the model is semi-distributed. So this is a sort of a compromise, as on the one hand, it recognizes that within a catchment, there are pollution hotspots. But on the other hand, it accepts that a fully distributed model representing the complete spatial structure of the catchment is desirable, but almost likely not going to be achieved mainly due to limitations in computing resources. So a semi-distributed model tries to make a pragmatic compromise and says, yes, there are going to be pollution hotspots in the landscape. We will try and model those pollution hotspots and their importance, but we won't try and do a complete representation of how all water and all pollutants move through a catchment. So I'd just like to put this into a bit of context. I said INCA is a process-based model. So there's three kinds of dynamic models, or three types of dynamic models. So the first is empirical. There are purely statistical relationships between variables of interest. There's no change in relationship over time. So one example of an empirical model might be a proxy relationship, such as we try and use between turbidity that we record from high frequency sensors and either suspended sediment or total phosphorus. So we use an empirical regression type relationship with these high frequency measurements to get a dynamic time varying assessment of suspended sediments or total phosphorus, but we don't have any ability to look at changes in the relationship over time. So proxies, an example of an empirical modeling approach, certainly very useful, but also limited, especially for long-term simulations. Process-based models represent relevant processes as low-order differential equations. So zero or first-order differential equation, zeroth order differential equation is like a constant change over time, whereas a first-order differential equation typically depends upon other variables of interest in the system, may have some environmental rate modifiers, say temperature or moisture controls on the soil processes. And one point I'd like to draw your attention to is that there's an idea that a process-based model represents relevant processes. So this comes to the idea that a model is designed by one or more individuals to represent their perceptual and conceptual models of how the world works. So certainly there's a lot of expert judgment goes into model design and some sort of selection of what is important or not important. And I think it is very important to remember that models are based upon a series of subjective judgments that go into their design and their establishment. That's not to say we cannot still obtain useful results out of them in many different areas, but a model is a product of a subjective decision-making process. The final class of models are physical or physically based models. These attempt to represent all processes using equations derived from first principles. So typically these will use theoretical equations for water flow in the soil, theoretical equations for chemical behavior, and are really very complicated models that I think have an important role to play from a research perspective, and may also be well used at a smaller scale. For example, at the scale of a soil profile, there's quite a bit of work with physically based models, and some useful insights come out of those. But at a catchment scale, it's my belief that a physically based model is simply too complicated to really use in any meaningful sense for decision making. They're certainly useful research tools, but they are too complicated to be applied in general widespread use. And on the other hand, say empirical models are really straightforward to apply, can certainly be useful for a dialogue with decision makers or stakeholders, but they miss the time varying properties, or that they may miss some of the key time varying properties of relationships in the system, so may give misleading or possibly spurious outputs. So it's certainly my perspective that the most appropriate type of dynamic model for catchment scale water quality simulations is a process-based model that tries to include relevant processes, represent them in a relatively simplistic manner, and aims for some sort of generality to be able to be used in as wide a range of situations as possible. So INCA, HYPE, and SWOT are all process-based models, all attempt to simplify or present a simplified conceptual model of the world that is still useful to support decision-making and understanding of the environment. Now, I'd also said that INCA's semi-distributed, so I'd like to just take a little tour through the kinds of approaches to spatial structure that are typically used in dynamic models. And the first of these approaches is the so-called lumped approach that effectively says there is no relevant spatial structure. Everything is modeled as one or more boxes or buckets that have no explicit spatial component. And this is the approach taken, for example, by the MAGIC model that has been widely used for both hindcasting and forecasting acidification effects. Lumped models are typically used when adding spatial structure would not really lead to any additional insight into process. And the designers of the MAGIC model felt that a lumped approach was acceptable, as they were mainly interested in, say, the long-term evolution of soil solution and lake water chemistry, and they didn't need to make a complicated spatial representation to do that simulation. So when spatial structure is not of relevance or importance for the question to hand, then lumped models are typically appropriate, as they give a simpler spatial representation. So this is easier to use and easier to interpret. When there is interest in some sort of spatial structure, like where in the catchment are pollutants coming from, or where are the hotspots where management actions should be focused, then a semi-distributed approach is appropriate, I believe. It gives some simplified representation of the spatial structure, at least, say, separating out different land cover types or different soil types, separating out the headwaters from the downstream areas of the catchment. There are two terms that you should be aware of for semi-distributed modeling. The first of these is the functional unit network. So it says that the building block in a semi-distributed model should be a soil compartment that can be defined based upon its chemical, biological, and hydrological processes. In reality, it should also probably be based upon the management that is applied to the soil, as for example, with at least nutrient modeling, whether a parcel of land is arable or pasture can have significant implications for the nutrient or pollutant fluxes out of that part of land. A similar term is the HRU, or hydrological response unit, derived from land use, soil, and slope. So both the FUN and the HRU are similar kind of concepts. They say that the landscape should be divided into some sort of mosaic of internally homogeneous elements. The FUN approach is embodied in INCA. The HRU approach is used in SWOT, but basically these are quite similar. They're saying that if one goes from a heterogeneous landscape, there should be some way of reconceptualizing that landscape as a series of homogeneous elements. And this greatly simplifies the way that a model runs. And with this simplification, there's faster runtime, more possibility to evaluate scenarios, more possibility to look at uncertainty. The final type of spatial structure is a distributed model. And this is, I guess, the typical example of this would be a GIS-based model. Typically, it would be grid-based. With a distributed model, there's a trade-off between spatial reality and process complexity, because a grid model needs to solve for many, many more units, say each grid cell, which might be thousands or tens of thousands, versus a semi-distributed model, which might have 10 or 100 units. The runtimes on distributed models can be quite slow. And one response to this from a model development perspective is to simplify even further the process representation in distributed models. So they generally have to simplify process representation just so they can run. So I'd again argue that kind of the sweet spot for catchment scale water quality modeling with a focus on decision support and evaluating policy decisions, the sweet spots at the semi-distributed level, which is neither too simple, the lumped approach, nor too complicated, the fully distributed approach. So INCA takes a semi-distributed approach to representing a catchment. As I said, there's 3 levels to this semi-distributed approach. Starting at level 1, the river catchment. If one has a GIS layer of the catchment with catchment boundaries, with river network, and with some sort of estimates of land cover, a catchment can be divided into subcatchments, and typically the division of subcatchments is made either where there are big changes in the way the river is flowing, or perhaps where there is a monitoring location, so it's possible to calibrate, or where there are sort of divisions of management interest. And if a whole river basin can be partitioned into a series of subcatchments, then these subcatchments can be divided into functional unit networks, and each of these functional units can then be conceptualized at the level 3 cell model. So all the biogeochemical processing and a lot of the relevant processes also for transport occur within this cell model, which is sort of repeated for each of the functional units in the system. And then the outputs of these functional units are summed up to generate what goes into the stream, the river network, which can then be summed up to what goes into the whole catchment, and then can be used to derive an assessment of pollutant fluxes throughout the river network and possible changes in fluxes in response to, for example, changing climate or changing management strategy. Now, there's a series of 5 generic components to the INCA model. And these are GIS interface. So this is more, I guess, of a recognition that there is a need to derive spatial data for setting up and running the model. And the amount of spatial data is relatively limited. At a bare minimum, for example, one would require catchment areas, but certainly the more information one has about land use and land cover, then the more realistic the model outputs are. Each version of INCA also has a pollutant input model to get the substance of interest into the modeling system. And typical inputs include atmospheric deposition. Many pollutants of interest have some sort of an atmospheric phase. As INCA has a background in sort of landscape scale diffuse pollution modeling, certainly fertilizer application is very relevant, and this can include, say, both organic and inorganic fertilizers. And all of these inputs can vary according to land use. So, for example, fertilizer typically only found in arable land, at least in Sweden. Atmospheric deposition varies depending upon land cover. For many pollutants of interest, there is higher deposition to forests than to other land cover types. So certainly there's all of the relevant types of pollution inputs can be simulated. For deposition, for many pollutants, there's both wet and dry deposition, which can behave differently in terms of its impact on the environment. So these can also be simulated. So the pollutant input model is basically gets the substances of management interest into the model. The third model component is a generic hydrological model, which simulates the flows of effective rainfall through the soils and into the river, and then flows in the river itself. So the hydrological model is really responsible for driving pollutant fluxes through the system. This includes both dissolved and particle-associated pollutants. You'll note that the hydrological model simulates based upon effective rainfall. So INCA is unlike most other water quality models insofar as the hydrological submodel is separated from the water quality submodel. And the effective rainfall is precipitation minus interception minus evaporation. So effective rainfall is rainfall that is eventually going to contribute to stream flow. This was a design decision with INCA early on, which I'll explain later, and it can be seen as either a strength or a weakness of the model. The fourth component is a terrestrial biogeochemical process model. So this is a series of equations describing transformations, mobilizations, losses, and retention within this, say, generic level 3 cell from an earlier slide. And the rationale of the terrestrial process model is to simulate all of the relevant processes for a pollutant that are occurring in the land. So this would include plant uptake, for example, of nitrogen, phosphorus, mobilization of any sort of soil associated pollutant, as well as sediment mobilization, microbial processes, which could be transformations or which might result, say, in losses to the atmosphere. So certainly atmospheric losses can be very important with a number of elements, specifically nitrogen, and as a class of compounds, also persistent organics. And the terrestrial biogeochemical process model also provides input to the in-stream process model. So the final generic model component is the in-stream process model, and it simulates the dilution of pollutants associated with water flows. It includes inputs of pollutants direct to the stream, so effluent from, for example, sewage treatment works or point source discharges. And it also simulates all in-river transformations and losses for some classes of pollutants like sediment or phosphorus. There's quite sophisticated routines describing sediment mobilization, settling, and transport throughout the river network.